Hello and welcome, ladies and gentlemen. We are looking at activity 4.1 here. We're just going to go ahead and jump right into it. So it says previously you made conjectures like this: if two parallel lines are cut by a transversal, then the corresponding angles are congruent. So it says you can also make conjectures about the converse of statements. The converse of an if-then statement is the statement that results from interchanging the hypothesis, the if part, and the conclusion, the then part of the original statement. So this type of statement is called an if-then statement because we have an if something happens, then another thing happens. Okay, the if part is also known as the hypothesis. Okay, and then the then part is also known as the conclusion, right? So the converse of a statement is just taking those two parts and flipping them. So to the converse of this, and we'll kind of talk about it in a second, or actually we'll just go ahead and do it right now. So this worked example has an example for us. I won't read the whole thing, but the number one here says write the converse of the conjectures stated above about lines and about parallel lines and corresponding angles. So if I wanted to write the converse of this, I would just take the second part, read it first, and then read the first part. So I would read if corresponding angles are congruent, then two parallel lines are cut by a transversal. So I'm just going to go ahead and write that. If corresponding angles, and there's my little sign for angles, are congruent, then two parallel lines are cut by a transversal. Sweet, so that is the converse of the statement because we just took the then part and made it our if. We took the conclusion, made it our hypothesis, and then we took the hypothesis and made it our conclusion. So number two here says, do you think both the original statement and the converse are true? Why or why not? So this one, we've talked, so parallel lines that are cut by a transversal look like this, right? And then corresponding angles are like 2, 3, 4, 5, 6, 7, 8. 1 corresponds with 5, 2 corresponds with 6, 3 corresponds with 7, 4 corresponds with 8, right? At these intersections, top left corresponds with top left. So you guys have seen this. So it's saying if corresponding angles are congruent, then two parallel lines are cut by a transversal. So we've learned about this. You guys learned about this in middle school. So you would just say yes, and then you could say you've learned about it before. You could say that you know it's true. You could draw a little picture. However you want to do that, it's good to go. But the answer we are looking for is yes in that case. So on this backside here, it says when a conditional statement and its converse are both true, then it is called a biconditional statement. A biconditional statement is a statement written in the form if and only if P, then Q. It is a combination of both a conditional statement and the converse of that conditional statement. So first thing says to think about, do you think that all conditional statements and their converses are biconditional statements? Do you think that every possible one is true both ways? Well, number 3, we get to explore that. So 3 says, consider the conditional statement. If Estelle goes out in the rain without an umbrella, she will get wet. So write the converse of that. So here's the if part. Here's our hypothesis. And then, and so they don't write then, but you can imagine if she goes out in the rain without an umbrella, then she will get wet, right? So then we want to switch this part. So we want to say if Estelle gets wet, then she went outside without an umbrella. So it says write the converse and then determine whether this is a biconditional statement. So if it's biconditional, that means that this part that we just wrote will also be true. So if Estelle gets wet, then she went outside, I guess outside in the rain without an umbrella. Okay, well, that's not the only way that this could happen, right? She could be maybe at a water park, it could be summertime, she could be hanging out at the lake, she could be hanging poolside, right? There's lots of ways for that to happen. So we would just go ahead and say that this is false. So the the first statement, the first if then was true, its converse was not true, so we said it was false, and then we would say it is not biconditional. Sweet. All right, number 4. David observed that the angles opposite the congruent sides of an isosceles triangle are congruent. He conjectured that if two sides of a triangle are congruent, then the angles opposite the congruent sides are always congruent. So basically, whenever you have an isosceles trapezoid, whenever you have an isosceles triangle, if you can locate your two congruent sides, so like he has these two that are congruent, then you can also locate the congruent angles because they will be opposite the congruent sides. So if here's one side, here's the angle that's opposite of it, and here's the other side, here's the angle that's opposite of that. And so the two angles that are opposite the congruent sides are congruent, is what he's saying. So then, do you think this conjecture is correct? Create isosceles triangles and use a protractor to measure angles to test David's conjecture. So to save some time, I just constructed one before. I'm going to say yes, I do think it's true. And then when I made a 90-degree angle here, and then I had 45 and 45. And so you can see that these two sides were the sides that I constructed as congruent. And so the opposite of this congruent side is this top angle, and the opposite of this left congruent side is this right angle. So you can see that this is in fact the case. And so create isosceles triangles and use a protractor to measures to test David's conjecture. So we'd say yes, and then like see pictures, right? Or see picture, depending on how many you have there. So easy peasy, here we go. Last one for 4.1. Question 5 says, write the converse of David's conjecture. Do you think the converse is true? How can you test the converse conjecture? So first thing is write the converse. So he says, so we'll go ahead and look up here. He says, if, so we're starting here, and then we're ending here. So he says, if two sides of a triangle are congruent, then the angles opposite the congruent sides are always congruent. So we would start by, to write all this out, we'd say if angles for opposite congruent sides in a triangle are congruent, then two sides of that triangle are congruent. All right, because he said if the angles opposite congruent sides are all, he said then the angles opposite the congruent sides are always congruent. So I said if angles opposite congruent sides of a triangle, I guess we don't know that they're congruent. So the way we'd want to write this is we'd want to say if angles opposite two sides of a triangle. So if angles opposite two sides of a triangle are congruent, then we could say those two sides of that triangle are congruent. And the reason I had to change my wording here is because we don't want to assume in the if part, this is the hypothesis, right? We don't want to assume that the two sides are congruent because we don't know that they are. We're saying if these angles that are opposite of the congruent sides, or if we're saying if angles opposite of two sides of a triangle are congruent, then those two sides are congruent. So I wouldn't want to say that they're congruent up here and then assume that they're congruent down here as well. So yeah, there you go. So that was the first part. Do you think the converse is true? So for that part, I'm just going to scoot this up now that we have the converse. Oops, if I can grab my paper. There we go. So do we think the statement is true? That's the first part. I would say yes. And then how could you test the converse conjecture? So if you wanted to, you could construct a triangle where you constructed two angles that were equal to one another using a protractor. And then you could connect all of the sides. So basically, if you constructed two angles that were congruent, say you made like this is just going to be an example. So say you made like a 30-degree angle and a 30-degree angle or something, right? We'll say these are both 30. And this is a bad example because it looks like a 45, 45, 90. But that would leave this last side to be 120 because we know that the interior angles of all triangles add up to 180. So if you made two angles that were congruent, then you could construct your triangle by knowing what this third angle made. And then you could check to see the opposite sides of your congruent angles and see if they are congruent, which I can go ahead and tell you they will be. So that is one way that you could test it. So then it has this little reminder here: testing a conjecture and proving it to be a theorem are not the same thing. Remember, a theorem has been proved true in all cases. So that's the main difference. Has been proved true in all cases here. Okay, and then a proof requires reasoning using definitions and theorems, whereas testing involves making observations, noting counterexamples, and using measuring tools, which is exactly what we did. So we just tested the conjecture. We did not prove anything yet. We will go ahead and do that later. But for now, I hope you all have a wonderful day. This was activity 4.1 here in our packet 4. Hope you have a good one, and I'll see you guys in class. Adios.